Hi everyone, I am Xiaokang Chen, a second-year master student at Peking University. Today I will share my paper, Semi-Supervised Semantic Segmentation with Pseudo Supervision. Nowadays, we could easily obtain massive amounts of data. However, it is hard and expensive to label the data, especially for the semantic segmentation task. For example, we could easily obtain the images of the city by taking photos, but it is hard to label each pixel carefully, such as the pole. There are mainly two solutions for the semi-supervised learning. The first is self-training, which is an offline process. The second is consistent learning, which is an online process. I will introduce them in the following. The first is self-training. There are mainly three steps in self-training. First, we train a model F on the labeled set. Second, we generate pseudo-labels for the unlabeled set. Third, we retrain a new model on the whole set, including ground truths from labeled set and pseudo-labels from unlabeled set. The second solution is consistency learning. The key idea is to encourage the network to give consistent predictions for unlabeled inputs that are perturbed in various ways. Here, the perturbations may include Gaussian noise, random rotation, color jittering, and so on. Here, I introduce a typical example of consistency learning, which I call it CPC. Give an input image X, we feed it into two different networks and get predictions P1 and P2. These two networks have same architecture but different initializations, so P1 and P2 are different. Then, we constrain the similarity between P1 and P2 through MSE loss. After the above pages, we have some knowledge about self-training and CPC. Self-training could expand the labeled set through pseudo-labeling, while CPC encourages the network to learn a compact feature space through consistency learning. So, how about the combination of them? This is what a CPS does. Based on the above findings, we propose the simple but effective framework CPS. We feed the input image X to two different networks, F-theta1 and F-theta2, getting two predictions P1 and P2. These two networks have the same architecture but different initializations. We use Chi-mean normal in PyTorch framework to initialize them. Then we generate one-hot labels from them, getting Y1 and Y2. The pseudo-label of the current network is used as the target of the other one. For example, Y2 is used as the target of P1, so this is a cross-separation with pseudo-labels. There are two roles of CPS. First, CPS encourages high similarity between the predictions of two networks for the same input image. Thus, the decision boundary lies in the low-density regions. Second, CPS expands training data by pseudo-labels. It is better than self-training because the consistency learning ensures a more compact feature space. Then let's see some results. Here is the Cityscapes dataset. We test our CPS on two models. The first is DeepLab V3 Plus, and the second is HRNet. The blue bar is the baseline, and the red bar is the CPS. Our CPS improves the very strong baseline significantly. Then we compare CPS with self-training. Here, blue bar means self-training and red bar means CPS. We could find that CPS consistently outperforms self-training. Then we compare CPS with CPC. CPS is better than CPC because the pseudo-label separation is better than the soft confidence separation. Here is the qualitative results. We could find that due to the labeled data is very few, the normally supervised method could not obtain accurate boundaries and the semantic information, where our CPS could handle this problem. Thank you for listening.